Any planned movement of material from one place to another using ropes, chains, hoists, or other types of equipment is called rigging. The term rigging refers not only to this movement, but also to the equipment used to accomplish the job. A simple block and tackle is one of the most basic devices that can be used to lift a load. A block and tackle allows you to lift an object much higher than would be possible with just your arms. In fact, a block and tackle can be used to lift an object to just about any height, provided that there is a supporting structure from which to hang the block and that the rope is long enough. In this part, we'll examine the components of a simple block and tackle. We'll also see how to inspect a simple block and tackle and how it can be used to lift a load. The basic parts of a simple block and tackle are a block and a rope. The block consists of a frame, a pulley called a sheave, and a support hook mounted on top of the frame. The support hook is used to hang the block from a supporting structure. The rope passes over the sheave and has a load hook attached to its end. The block can be thought of as dividing the rope into two sections. One part of the rope is attached by the load hook to the load to be lifted. This part is referred to as the load line. The other part of the rope is pulled by the rigger performing the lift. This part is called the hauling line or the fall line. Before any load is lifted, it's important to determine whether the lift can be performed safely. The first step in making this determination is finding out how much the load weighs. In some cases, the load's weight is stamped directly on the load, or the weight may be stamped on a nameplate attached to a piece of equipment. For a load of material, you may have to check the manufacturer's specifications or use standard weight charts to estimate the weight. Once you know how much weight you'll be lifting, the next step is to select the correct block and tackle for the job. The block must be the right size and type for the rope you'll be using, and the rope that's chosen must have a breaking strength that provides the approved safety factor as outlined in your company procedures. Breaking strength is the maximum load a rope can lift before it begins to break apart. Once you've assembled the needed equipment, the next step is to carefully inspect the block and tackle for any signs of excessive wear or damage. After you've thoroughly inspected the equipment, the next step is to select an overhead support from which to hang the block. The support structure must be able to support the weight of the load, the block and tackle, and the force you'll exert to lift the load. In this example, the support hook is used to hang the block from the structural beam in this covered work area. Once the block is securely hung overhead, attach the load hook to the load. To lift the load, grasp the hauling line firmly in both hands. Set your feet about shoulder width apart and pull down in a smooth, even motion, keeping your back straight. At the end of the downward pull, hold the rope in one hand while you move your other hand up the rope to establish a new grip, and pull again. Continue this process until the load is at the desired height. A block and tackle, like most machines, makes it possible for you to perform more work than would be possible without it. A block and tackle is able to do this because it provides a mechanical advantage. In general, mechanical advantage is defined as the advantage gained in transmitting force through the use of a machine. This advantage is expressed as a ratio. The ratio compares the force that the machine applies to a load to the force that you apply to the machine. To calculate mechanical advantage for a simple block and tackle, we divide the weight of the load by the force that's required to hold the load. For a simple block and tackle, the mechanical advantage equals 1. That means the force required to hold the load equals the weight of the load. Although a simple block and tackle allows the rigger to lift a load high above his head, it doesn't provide any advantage in terms of lifting capacity. In fact, the mechanical advantage of 1 that a simple block and tackle provides considers only the effort required to hold the weight. If a rigger wants to use a simple block and tackle to raise a load, more effort will be required. A compound block and tackle uses 2 or more blocks and pulleys called sheaves to create a greater mechanical advantage than a simple block and tackle. For example, this compound block and tackle has 2 blocks and 5 sheaves. Multiple sections of rope called parts are threaded or reeved through the sheaves. The rope sections or parts are reeved or threaded through the two blocks in such a way that each part of the rope supports a portion of the load weight. In this example, the block and tackle arrangement creates 5 parts of rope. If the block and tackle were 100% efficient, each part would support exactly 1/5 of the total weight of the load. But some loss of efficiency always occurs in a block and tackle. An important part of selecting the right compound block and tackle to lift a load is determining how many parts of rope you need. To do this, you can use a formula for calculating a value called the efficiency factor. The efficiency factor is a reference value that can be looked up in a conversion table to determine how many parts of rope are required to create the mechanical advantage you need. But before you can use the formula, you have to gather some information. First, you need to know how much weight you can comfortably lift. Whenever you perform a lift, you may be required to hold the load suspended in air while it's repositioned. So your lifting capacity must also take into account your ability to hold the suspended load for a period of time. There are several ways to determine your lifting capacity. One method is to rely on personal experience. Over time and several lifts, you'll probably develop a good sense of your capacity. Another method is to make several test lifts with a simple block and tackle. Begin with a lightweight object, then test lift heavier loads until you reach a weight that's difficult to lift and hold. The weight of the load in your final test lift will equal your lifting capacity. Another method for testing your lifting ability is to attach a device called a dynamometer to measure the amount of force exerted as you pull against it. Before you can use the formula to calculate the efficiency factor, you need one other piece of information. In addition to knowing your lifting capacity, you also need to know the weight of the load. The load weight may be stamped on the load itself or on an identification plate. It may also be listed on a shipping label or in the manufacturer's specifications. But for some loads, you may need to estimate the weight or weigh the load on a scale. Once you know your lifting capacity and the weight of the load, you can use the formula to determine the efficiency factor. Let's look at an example to see how it works. In this example, the load weighs 312 pounds. Our rigger knows that he can comfortably lift 80 pounds. The weight of the load divided by the lifting capacity of the rigger equals the efficiency factor. In our example, 312 divided by 80 gives us an efficiency factor of 3.9. Next, the rigger must look up the efficiency factor in a conversion table to see how it corresponds to the number of parts of rope in a compound block and tackle. In this table, our calculated efficiency factor of 3.9 falls in between the values for 4 and 5 parts of rope. To be on the safe side, always round up to the higher number. So in our example, the rigger would need a compound block and tackle with 5 parts of rope. A key point to remember is that blocks must be chosen so that their sheaves will equally distribute the weight of the load when the rope is properly reeved through them. So for our example load, the rigger needs 2 blocks that will create 5 parts of rope when they're properly reeved. To do this, he selects a block with 3 sheaves and a block with 2 sheaves. In this part, we'll examine the basic parts and function of a compound block and tackle. Then we'll see how a compound block and tackle can be set up and used to lift a load. A typical compound block and tackle has an upper block called the fixed block and a lower block called the movable block. The fixed block has a support hook attached to its frame for hanging the block and tackle. The movable block has a load hook underneath the block for attaching to the load. Each block has grooved pulleys or sheaves that guide the rope as it passes through the block. In this configuration, the movable block has a device used to tie off the end of the rope. You may hear this device referred to as a becket. The sections of rope that pass through the blocks are called parts or falls. Each part of rope in the compound block and tackle supports a portion of the total load weight. The section of rope that's pulled to begin the lifting process is referred to as the hauling line. You may also hear this section of the rope called the hoisting line, the fall line, or the running part. The other end of the rope is tied off to one of the blocks. This end is commonly known as the dead end. After the lift planning session, the next step is to select the appropriate block and tackle for the job. Blocks should be selected so that they will create the appropriate number of parts of rope. A key point to remember is that blocks should be chosen so that their sheaves will equally distribute the weight of the load when the rope is properly threaded through them. If the number of sheaves in the blocks is balanced, the number of parts of rope created will always equal the number of sheaves. For example, to create 5 parts of rope, you would choose one block with 3 sheaves and one with 2 sheaves. When the rope is threaded through these blocks properly, it will create 5 parts of rope. In order for a compound block and tackle to work properly, it's essential that the rope be threaded through the sheaves in the correct manner. This is called reeving the blocks. Because there are so many possible combinations of blocks and sheaves, it would be impossible to show all of the different reeving patterns. So, anytime you have to reeve a new compound block and tackle, you should check a rigging handbook or the manufacturer's instructions, or ask your supervisor for the appropriate reeving diagram. To get an idea of how this is done, let's look at an example of a typical reeving process. This compound block and tackle has a fixed block with 3 sheaves and a movable block with 2 sheaves. When properly reeved, it will create 5 parts of rope. To reeve this block and tackle, the rigger begins by passing the rope through the center sheave on the fixed block. Then he passes it through one of the sheaves on the movable block. Next, he passes the rope through one of the outside sheaves on the fixed block. Then through the other sheave on the movable block. Next, he passes the rope through the other outside sheave on the fixed block. To complete the reeving, he ties the rope off to the becket on the movable block. In our example, the total number of sheaves, 5, is an odd number. When the total number of sheaves is odd, the dead end of the rope is tied off to the becket on the block that has the smaller number of sheaves. In most cases, that's the movable block. If the total number of sheaves is an even number, the dead end of the rope is attached to the becket on the fixed block. When you finish reeving a set of blocks, there are a few checks you can make to ensure that the blocks are reeved properly. Make sure that the hauling line leads from the center sheave of the fixed block. And make sure that the 2 blocks are at a 90-degree angle to each other. Finally, inspect the entire block and tackle again. Make sure that the rope moves easily through the blocks and that everything seems ready to go. After this final check, the block and tackle can be used to perform the lift. The support hook is attached to the overhead support. Then the load hook on the movable block is attached to the load. To lift the load, the rigger pulls on the hauling line. As the load is lifted, the rigger watches the load and block and tackle to ensure that the lift is occurring properly. One of the most common types of lifting devices you're likely to use is a hoist. A hoist is a small, portable device that can be attached to an overhead structure, such as a beam, and used to lift a load. Hoists are designed primarily for straight, vertical lifts, and they're often used when there's no room for a crane or other large lifting device. Here's an example of one type of hoist. It's called a chain hoist or chain fall. A chain hoist uses a set of gears to provide the mechanical advantage that's needed to lift a load. We'll use this example to get an idea of how one type of chain hoist works. This chain hoist consists of a housing called a body and 2 chains. One chain forms an endless loop called the hand chain. The other chain is a single length of chain or wire rope. It's called the load chain. Inside the body of the chain hoist are 2 sheaves. One sheave, called the hand wheel, connects to the hand chain. The other sheave, called the load wheel, connects to the load chain. The 2 sheaves are connected to each other through a set of gears. The hand wheel is connected to a small gear. This small gear meshes with a larger gear that's connected to the load wheel. The difference in gear size provides the mechanical advantage in the hoist. Now let's see how riggers can use the hoist to lift a load. After carefully planning the lift and inspecting all the equipment, the riggers are ready to use the chain hoist to lift a load. First, the chain hoist is hung from an overhead support. Next, the load hook is attached to the load. When they're ready to start the lift, one rigger pulls on the hand chain. The other rigger stands beside the load and helps steady it to prevent the load from swinging or rotating out of position. As the rigger pulls the hand chain, links of the chain fit into pockets in the hand wheel, causing it to turn. The pockets in the hand wheel ensure that the chain turns the hand wheel at a constant rate. The pockets also prevent the hand wheel from slipping. Inside the body of the chain hoist, the hand wheel turns the gear attached to it. This gear meshes with the larger gear on the load wheel, causing it to turn. As the load wheel turns, the load chain is pulled through the chain hoist body, and it raises the load. Excess chain hangs below the body in a loop called the tail chain. The end of the tail chain is connected to the body of the hoist to prevent the load chain from feeding completely out of the body. Most chain hoists also have a ratchet mechanism inside the body. The ratchet acts as a brake to hold the load in place as it's being lifted. Some chain hoists use an electric or pneumatic motor to drive the hand wheel. Motorized hoists are often used in situations where repeated lifts are made. The motor is controlled from a remote control panel, which is often called a pendant controller. Motorized chain hoists can raise and lower loads faster than hand-operated hoists. However, they can only be used where a source of electricity or compressed air is located nearby. Another commonly used type of hoist is a come-along or ratchet lift. A come-along uses a handle and ratchet mechanism to move a load chain through a body and lift a load. Another commonly used type of hoist is a come-along or ratchet lift. A come-along uses a handle and ratchet mechanism to move a load chain through a body and lift a load. The body contains the ratchet mechanism, a ratchet handle, and a ratchet release lever. The ratchet release lever allows the rigger to change the direction of the chain movement through the body. If the lever is set in the middle position, the chain can be pulled freely through the body. A support hook on top of the body is used to hang the body from an overhead support. The load chain and load hook are used to connect the come-along to the load. A wheel called a fast wind handle allows the load chain to be moved through the body quickly to take up slack in the load chain. Now let's watch as a rigger uses the come-along to lift a load. In this example, the rigger has already hung the come-along from a sturdy overhead support. To begin the lift, the rigger sets the ratchet release lever to the middle position. This allows the load chain to be pulled through the body of the come-along. Next, he attaches the load hook to the load. Now the rigger is ready to take up the slack in the load chain. To do this, he releases the fast wind handle and pulls the load chain through the come-along. Another method of taking up the slack is to set the ratchet release lever to the raise position. Then turn the fast wind handle or pump the ratchet handle to raise the chain and take up the slack. When the slack is out of the load chain, the lift can begin. First, check to ensure that the ratchet release lever is in the raise position. Then the ratchet handle is pumped back and forth. As the handle is pumped, the ratchet mechanism inside the body moves the load chain through the body and raises the load. To lower the load, the rigger sets the ratchet release lever to the lower position. Then he pumps the ratchet handle to lower the load. Jacks are small portable lifting devices that use leverage or hydraulic pressure to lift and support a load. Unlike hoists and winches, which lift from above, jacks are typically placed underneath a load. And most jacks are designed to raise a load only a short distance. In this part of the program, we'll take a look at several different types of jacks. We'll look at ratchet jacks, screw jacks, and hydraulic jacks. We'll start with ratchet jacks. When a ratchet jack is used to lift a load, the jack is placed underneath the load. As the hand lever is moved down, the lifting pawl engages a tooth in the rack bar and forces the bar to move up. At the bottom of the hand lever stroke, the holding pawl engages another tooth on the rack bar. The holding pawl holds the rack bar in position as the hand lever is moved back up. At the top of the stroke, the lifting pawl engages another tooth on the rack bar, and the process can be repeated. Another common type of jack is a screw jack. A screw jack, or bottle jack as it sometimes is called, is basically a screw inside a casing. The jack lifts the load as the screw is turned. When the handle on the screw jack is turned, the threads on the outside of the screw mesh with the threads on the inside of the jack casing. This causes the screw to raise or lower, which also raises or lowers the load. The next type of jack we're going to look at is a hydraulic jack. Hydraulic jacks use a pressurized fluid, such as oil, to raise or lower a load. A hydraulic jack uses a pump to pressurize fluid that's stored inside a reservoir. The fluid is then pumped from the reservoir into an area below a piston. The force of the fluid being pumped into the jack causes the piston to raise up and lift the load. When the pressure release valve is opened, the pressure on the hydraulic fluid is released. The weight of the load then forces the piston to retract and the load is lowered. Some hydraulic jacks have an internal pump, while others have an external pump. When a hydraulic jack is used to raise a load, the jack is placed underneath the load so that the load cap is positioned directly below the lifting point on the load. Then the hand lever is moved up and down to operate the pump. The pump pressurizes the fluid and forces it into the area below the ram, and the ram raises the load. To lower the load, the pressure release valve is opened. As the pressure on the fluid is released, the weight of the load forces the ram to retract, and the load lowers. A hydraulic jack that has an external pump operates in exactly the same way. The difference is that the pump and the fluid reservoir are located outside of the jack. The pump and reservoir are connected to the jack by a hose. When the pump is operated, the pressurized fluid is forced through the hose and into the area below the ram. Some hydraulic jacks are powered by a gasoline engine or an electric motor rather than by a hand lever. On these jacks, the motor or engine is usually mounted on top of the reservoir. In this part, we'll take a look at winches and see how they can be used to lift a load. A winch is a device that's designed to lift and move a load using a wire rope or a chain. Some winches are hand-powered, but for lifting most loads, you'll use a motor-driven winch. This winch uses a pneumatic motor to turn a drum. Wire rope wrapped around the drum is then reeled in or out to raise or lower a load. You may hear a winch like this one referred to as a tugger or a chugger. The basic parts of this winch are a motor control switch, a drum brake, and a wire rope called the load line. The load line has an eye at the end. The eye is used with rigging hardware to attach the load line to the load. This winch is designed so that the load line comes off the drum horizontally. Rigging hardware redirects the load line up to a simple block and tackle mounted overhead. Before operating the winch, the rigger must securely mount the winch in place to prevent it from sliding along the floor as the load is pulled. Sometimes a winch can be bolted directly to the floor, but in this example, the rigger will secure the winch to the foundation of a steel beam. First, he attaches a sling to the winch and wraps the sling around the beam. Next, he places wooden blocks between the sling and the sharp corners of the foundation to prevent the sling from being damaged. These blocks are called wear pads or softeners. Once the winch is securely in place and the rigger has connected the air supply to the pneumatic motor, he tests the controls on the winch. The test includes checking the winch's operation in both directions, as well as checking the brake. When the rigger is sure that the winch is functioning properly, he attaches the load line to the load. After receiving the signal to begin the lift, the rigger sets the motor control to the lift position and releases the brake. As the motor turns, it rotates the drum and reels in the load line, lifting the load. When the load reaches the correct height and the stop signal is given, the rigger applies the brake and stops the motor. To lower the load, the rigger sets the motor control in the lower position and releases the brake. He lowers the load until he receives the stop signal. Then he applies the brake and sets the motor control in the stop position. Once the load is completely lowered, the rigger disconnects the load line from the load. Then he reels the load line back onto the winch drum. Finally, he disconnects the winch's air supply and removes the sling that secures the winch to the steel beam. In this topic, we examined some common lifting and supporting equipment. We saw how hoist and come-alongs can be used to lift a load from above, and we saw how jacks can be used to lift and support a load from below. We also took a look at winches, and we saw how they can be used to lift a load. Let's pause now so you can try some practice questions on this material. In this part, we'll take a look at slings, and we'll see how they can be used in rigging a load. We'll also see how sling angles affect the lifting capacity of a sling. A sling is a device that's used to attach a load to a lifting device, such as a hoist or crane. Slings are commonly made of wire rope, chain, or synthetic fiber. An important part of using any sling is choosing the correct sling for the job. One factor that affects how much weight a sling can hold is the lifting capacity of the sling. An important point to keep in mind is that the rated lifting capacity of a sling is the amount of weight that can be lifted by a new sling that's used in an approved hitch pattern. The rated lifting capacity also depends on the angle at which the sling is rigged. Information about the rated lifting capacity of a sling can usually be found on a tag attached to the sling or in the manufacturer's manual. For example, this sling is rated to hold 5,300 pounds when it's used in a vertical hitch. But when the sling is used in a choker hitch, the rated capacity drops to 4,200 pounds. When the sling is used in a basket hitch, the rated capacity actually increases to 10,600 pounds. Let's take a closer look at how hitch patterns affect the rated capacity of a sling. This is an example of a sling rigged in a single-leg vertical hitch. A vertical hitch pattern is used when the sling will lift a load straight up. In this type of hitch, the sling carries the full weight of the load. In our example, the sling is able to carry loads up to 5,300 pounds. When the sling is combined with other slings in a bridle hitch, each sling carries an equal portion of the load. However, when this sling is used in a choker hitch, its rated capacity is only 4,200 pounds. The rated capacity is reduced when the sling is used in a choker hitch because of the tight bend created as the sling material passes back through the eye loop at one end of the sling. This sharp bend in the sling material causes the fibers or wires on the outside of the sling to stretch, while the fibers or wires on the inside are compressed. As a result, the sling material on the outside supports more of the weight of the load than the sling material on the inside. On the other hand, when a sling makes a large turn, as it does in this basket hitch, there is no increase in the strain on the sling material. In fact, this hitch pattern actually decreases the strain on the sling. When a basket hitch is used, the sling acts as if it were two separate legs supporting the load. That's why when this sling is used in a basket hitch, its rated capacity doubles to 10,600 pounds. Another key factor that affects the amount of weight a sling can safely support is the sling angle. In this example of a two-leg bridle hitch, the sling angle is the angle between the sling and the imaginary vertical line from the lifting point straight down to the load. As the sling angle is increased, the tension placed on the sling also increases, and the amount of weight that the sling can handle decreases. Let's look at some examples to see how sling angles affect the lifting capacity of a sling. In this illustration, the load to be lifted weighs 1,000 pounds. Two slings connect the load to a lifting beam. A device called a dynamometer is attached to each of the slings to measure the force that's placed on the sling. When the load is lifted with these vertical hitches, the sling angle is 0. The force on each sling is 500 pounds. But when the lifting beam is eliminated and the two slings are attached to a single lift point, the forces change with the sling angle. Here, the slings are connected so that each sling is at an angle of 30 degrees. The force created by the 30-degree sling angle is 577 pounds on each sling. If the sling angle is increased to 45 degrees, the force increases to 707 pounds. And if the sling angle increases to 60 degrees, the force goes all the way up to 1,000 pounds on each sling. With a 60-degree sling angle, the force placed on each sling is equivalent to the total weight of the load. If the sling angle increases to 80 degrees, the force on each sling jumps up to 2,880 pounds. A chart listing common sling angles and their effects on sling lifting capacity can be found in most sling manufacturers' literature. Typically, sling manufacturers recommend keeping the sling angle under 45 degrees. One way to change the sling angle is to change the length of the sling used in a lift. Let's look at an illustration to see how sling length affects sling angle. In this example, 2 slings are used to lift this load. Each of the slings is 7 feet long and at an angle of just about 60 degrees. If the sling length is increased to 8½ feet, the sling angle changes to approximately 45 degrees. If the slings are further lengthened to 12 feet, the angle is reduced to 30 degrees. One important aspect of safely lifting any load is ensuring that the load is balanced. When an unbalanced load is lifted, it could tilt or swing. If the load shifts suddenly, it could be dropped. To prevent this from happening, all loads should be lifted with the lifting device directly over the load's center of gravity. A load's center of gravity is the point at which its weight is concentrated. When an unbalanced load must be lifted with slings, the lengths of some of the slings must be adjusted so that the lifting device will be directly above the load's center of gravity. One device that can be used to balance a load is a turnbuckle. Turnbuckles can be used to make small adjustments in the lengths of sling legs. Lengthening the slings on one side of the load will shift the lift point over the load's center of gravity. A turnbuckle is a device that consists of a threaded body and 2 screw ends. The screw ends are threaded in opposite directions from one another. Because the 2 screw ends are threaded in opposite directions, the turnbuckle shortens when its body is turned in one direction and lengthens when its body is turned the opposite way. To keep a load balanced, it's important to select slings that are as close to the correct length as possible. Then use turnbuckles to make any small adjustments that may be necessary to balance the load. When you choose a turnbuckle, you must consider its lifting capacity. The capacity of a turnbuckle is determined by the diameter of the threads on its screw ends and by the types of screw ends that are used. The larger the diameter of the threads on the screw ends, the greater the lifting capacity of the turnbuckle. Turnbuckles are typically not marked to indicate their capacity. To determine a safe working load for a turnbuckle, you should check the manufacturer's manual. When a turnbuckle is used, one screw end is typically attached to the load hook on the lifting device, and the other screw end is attached to the sling. Then the body of the turnbuckle is rotated in the appropriate direction to either lengthen or shorten the length of the sling. Another leveling device is a load leveler. It's used when fairly large adjustments must be made in the lengths of the legs in a hitch pattern. This illustration represents a typical load leveler. The load leveler has a body with a support eye mounted on top, 2 chain legs, and 2 load hooks. A hex adjuster on the side of the load leveler's body connects to an internal worm and roller gear, which turns a chain sheave. The chain sheave is a sheave with pockets to pull the links in the chain legs through the body of the load leveler. When the load leveler is used, the support eye is hung from the load hook of a lifting device. Then each chain leg is hooked to a lifting point on the load. To adjust the leg length, the hex adjuster is turned with a wrench. The hex adjuster turns the worm and roller gear. The worm and roller gear turns the chain sheave. As the chain sheave turns, pockets in the sheave pull the links in the chain legs through the body. This causes one leg of the chain to lengthen while the other leg shortens. Lengthening one leg and shortening the other positions the lifting point directly over the load's center of gravity. In this topic, we saw why sling capacity must be considered when slings are chosen for a lifting job. We also saw how the rated capacity of a sling can change depending on the hitch pattern used for the lift and the angle at which the sling is rigged. We also looked at 2 leveling devices that can be used to help balance a load. Let's stop now so that you can try some practice questions on this material.